The ESO Very Large Telescope Array, the flagship project of European astronomy for the next millennium. Based on a host of innovative ideas, the application of advanced optoelectronic systems and sophisticated software, it represents a revolution in design, construction and operation of an astronomical telescope. The Very Large Telescope, or VLT for short, is currently being erected on Cerro Paranal in the Chilean Atacama Desert. It's an array of giant unit telescopes that can work together, functioning as one single optical telescope, the largest on planet Earth. Soon, ESO, the Intergovernmental European Research Organization behind the VLT, will put the first of the VLT unit telescopes into operation. The basic task of an optical telescope is to collect the sparse light particles from remote celestial objects. Coming from the depths of space, the light is reflected and focused by the telescope's optical system, the primary, the secondary, and the tertiary mirror. The larger the primary mirror is, the more light it can collect. Each of the VLT primary mirrors is 8.2 meters in diameter, enormous pieces of glass. In order to keep the weight of these mirrors to a minimum, they're very thin, only 17.8 centimeters in thickness. A mirror of such dimensions is no longer stiff. Under the effects of gravity and wind, it will twist and bend. It can only be used for astronomical applications if it's placed in a cell with an adjustable support system, which will keep the mirror in its optimal shape and position at all times. This idea, developed at ESO and known as active optics, has led to the design of a mirror support system actively controlling the mirror shape and position with a precision in the order of 50 millionths of a millimeter. Active optics has caused a revolution in telescope design. The mirror cell supports the primary mirror axially and laterally. It's fitted with an elaborate system of actuators and support pads, evenly distributing the mirror weight. The M1 cell is a welded metal structure attached by 12 flanges to the telescope tube. On the cell's upper side, the primary mirror is positioned and held in place by axial and lateral supports. The axial supports consist of a passive and an active part. The passive system with 150 hydraulic pads, the active system with 150 electromechanical actuators. These actuators are used for the active optics system. During observations, active optics relies on real-time analysis of the actual star image as produced by the telescope. From the appearance of the star image, the optical aberrations are deduced and corrective signals are sent to the electromechanical actuators, each of which can move up or down independently of each other. By proper adjustment of the mirror shape, a perfect image can be obtained. But the temperature of the mirror, too, must be carefully controlled. Even small temperature differences between the mirror and the ambient air can cause air turbulence, which reduces the image quality. The mirror cell contains a cooling system in order to keep the mirror temperature at the same level as that of the environment. This cooling system is placed just underneath the primary mirror. It consists of a large cooling plate that removes heat by infrared radiation without physical contact with the mirror. The cell of the primary mirror also supports the tower that holds the tertiary mirror, which sends the light into the telescope Naismith focal points. On the underside of the cell, there's an attachment flange for the Cassegrain adapter rotator. The development of the mirror cell, with its unique combination of electromechanics, hydraulics, electronics, and its telescope and instrumentation interfaces, was a time-consuming task. On the basis of ESO's experience with active optics systems, Preliminary performance specifications were determined, and ESO specialists carried out structural computations and tests of electromechanical actuators based on different design solutions. Then, engineers at ESO and European industry joined forces to quickly arrive at a mature product fulfilling the technical and scientific requirements. Facing strong competition, GIAT Industries, in collaboration with SVIM Industries, another French company, was awarded a design and development contract for the M1 cell. The task was the complete design of the system and its verification by means of test benches, including the construction of a full-scale cell mock-up. On the basis of analysis and models, ESO's engineers were now able to verify the feasibility of the unique design concept proposed by GIAT. In view of the complex hydraulic and electronic systems that were to be installed inside the cell, easy access and plenty of space inside the structure were considered to provide a significant advantage over rival designs. The design of the cell is based on laser cutting and welding technology, of which GIAT Industries is a leader in Europe. The specific advantage of this technique is its capability of producing very complicated structures starting from thin metal sheets. Thus, it's possible to produce large beams with very thin walls. This means very high stiffness at a low weight. In fact, the entire M1 cell, designed to carry the weight of a 23 metric ton mirror, 4.5 tons of Cassegrain instrumentation, and a multitude of electronic devices, only weighs 11 tons itself. Its deflection and natural frequency is compatible with the overall telescope performance. The M1 cell was assembled with the upper face down, starting from the individual laser welded assembly. It was machined with specially built equipment on both the superior plane, where the mirror supports are located, and on the inferior flange, where the Cassegrain instrumentation is attached. This necessitated the M1 cell being turned several times during the assembly phase. To guarantee tight dimensional tolerances, the final control of the M1 cell was made with optical theodolites. In advance of final production, pre-series models of the primary mirror supports were made and extensively tested. Before delivery of the equipment for final integration in the M1 cell, the complete equipment was once again fully tested, and records are kept to compare and monitor its performance during its operational life. March 1997. Less than a year before the first VLT unit telescope goes into operation. On a sunny morning, the time has come for the first test integration of the primary mirror in the cell. For this purpose, a dummy mirror made of concrete is used. However, its dimensions, weight and other main mechanical features exactly resemble those of the real VLT mirror. This test integration demonstrates the procedure of safely introducing the huge primary mirror in the M1 cell. In addition, this is the start of a period of intensive trials, during which the functions of the equipment are thoroughly tested before shipment to the remote Paranal site in Chile. The successful development and construction by GIAT of the mirror cells for the ESO VLT is a convincing example of the fruitful collaboration between ESO and European industry. It provides a stimulus and an opportunity for Europe's industries to prove their high-tech capabilities and competitiveness in increasingly important new areas of civil applications. Based on these novel technological concepts, the new generation of telescopes will undoubtedly pave the way for breathtaking discoveries. Being the largest and most versatile of the new telescopes, the ESO VLT will give Europe's scientists a front seat in the exploration of the universe.